It started as background noise. Dr. Artem Burdanov was analyzing images from the James Webb Space Telescope, studying distant planets orbiting a star called TRAPPIST-1. For most astronomers, the small streaks of light crossing the frame were nuisances, asteroids photobombing their data. But Burdanov saw something different. He saw an opportunity to find what had been invisible until now. The smallest asteroids in the main belt, some no bigger than a school bus, hidden in plain sight between Mars and Jupiter. What his team discovered would change our understanding of planetary defense and reveal that the asteroid belt is far more crowded than anyone imagined. But before we dive into how they found these invisible space rocks, you need to understand why we've been flying blind for so long. The main asteroid belt stretches across a vast region between Mars and Jupiter, roughly 200 million kilometers wide. It contains millions of rocky fragments, remnants from the solar system's violent formation 4.6 billion years ago. For 2 centuries, astronomers have catalogued these objects, mapping over 1 million asteroids. But there was a problem. Ground-based telescopes could only detect asteroids down to about 1 kilometer in diameter. Everything smaller remained invisible, a blind spot in our understanding of the solar system. This size range matters enormously for planetary defense. Smaller asteroids, measuring just tens of meters across, strike Earth far more frequently than their massive counterparts. The 2013 Chelyabinsk meteor in Russia was only 18 meters wide, yet it exploded with the force of 30 Hiroshima bombs, injuring almost 1,500 people. These asteroids are difficult to track because they're small and dark, absorbing most visible light. By the time we spot them, they're often already dangerously close. The James Webb Telescope wasn't designed to hunt asteroids, but Webb has a unique advantage. It sees in infrared wavelengths. While asteroids barely reflect visible light, they glow brightly in infrared as they absorb and remit the sun's heat. This makes Webb unexpectedly powerful for asteroid detection. So how did 2 scientists at MIT turn Webb into an asteroid hunting machine? It all started with data that everyone else was throwing away. Artem Burdanov and Julian DeWitt, planetary scientists at MIT, were working with Webb data collected to study the TRAPPIST-1 star system. The telescope had captured over 10,000 images of the star, staring at the same patch of sky for hours at a time. Hidden in those images were asteroids passing through the frame, tiny moving dots that most researchers would filter out as interference. Instead of discarding them, the team developed a computational technique called shift and stack. The method works by shifting images in every possible direction and at every speed an asteroid might travel, then stacking them to amplify faint signals. During the COVID-19 pandemic, when lab work slowed, Burdanov had time to experiment. He joked that while some people learned to make sourdough, he learned to find asteroids. The technique worked. While processing Webb's TRAPPIST-1 data, the team identified 8 known main belt asteroids as a proof of concept. Then they pushed further, searching for objects below the detection threshold of any previous survey. What emerged stunned them. 138 previously unknown asteroids, all measuring between 10 and 100 meters in diameter, the smallest main belt asteroids ever detected. Some were barely larger than a bus, others stretched to the size of a football stadium, but all were too small and too dark for ground-based telescopes to have ever spotted. Now here's where this discovery gets really important. These tiny asteroids aren't just sitting peacefully in the belt. This discovery fills a critical gap in our knowledge of the solar system. Larger asteroids in the main belt tend to stay in stable orbits, held in place by Jupiter's gravitational influence. But smaller asteroids are more vulnerable to perturbations. Solar radiation pressure, subtle gravitational nudges, and even the Yarkovsky effect can alter their paths over time. These small bodies are far more likely to escape the belt and migrate inward, becoming near-Earth objects. Understanding the population of these asteroids helps planetary defense efforts calculate impact probabilities. We now know these smaller asteroids outnumber their larger cousins by enormous margins. The MIT team's findings suggest the main belt contains vastly more small objects than previous models predicted. That means more potential impactors could be heading our way over the coming centuries, and we need better tracking systems to spot them early. Webb's infrared capabilities proved transformative for this work. Traditional surveys rely on reflected sunlight, which makes dark asteroids nearly impossible to detect. But asteroids are much brighter in infrared wavelengths, making them easier to spot against the cold background of space. The methodology opens new possibilities for mining archival data. Webb has collected thousands of hours of observations for various scientific purposes, all potentially containing undetected asteroids. They estimate thousands more small asteroids could be hiding in existing data, waiting to be discovered. And it's a good thing they figured this out when they did, because late last year, we got a wake-up call. The value of this research became urgently clear in late 2024 when astronomers discovered asteroid 2024 YR4. Initial observations suggested the roughly 60-meter-wide space rock had a small but concerning chance of impacting Earth in 2032. At one point, estimates placed the probability as high as 3.1%, the highest ever recorded for an object this size. An impact would have been catastrophic, potentially destroying an entire city with the equivalent force of hundreds of nuclear weapons. Webb was called into emergency service. Using the same infrared techniques developed by the MIT team, astronomers precisely measured the asteroid size, thermal properties, and trajectory. The observations revealed 2024 YR4 is approximately 60 meters across with a fast rotation rate and a rocky surface composed of fist-sized or larger chunks. The Webb data improved orbital predictions by nearly 20%, allowing scientists to conclusively rule out Earth impact. The asteroid poses no threat to our planet in 2032 or beyond. More importantly, the observations demonstrated Webb's capability to track small, potentially hazardous asteroids, even after they've moved too far from Earth for ground-based telescopes to follow. But the story doesn't end with planetary defense. These discoveries are revealing secrets about our solar system that have been hidden for billions of years. Beyond planetary defense, these discoveries help astronomers understand the asteroid belt's evolution. Small asteroids are fragments from larger bodies, shattered by collisions over billions of years. The abundance of these objects reveals information about collision rates, impact physics, and how material has been redistributed throughout the belt's history. Webb's accidental role as an asteroid hunter also highlights the value of serendipitous discovery in astronomy. The telescope's failed calibration images yielded valuable scientific results when examined with fresh eyes. One European team found a 100 to 200 meter asteroid in the same manner, accidentally captured during calibration. The discovery suggests Webb will continue finding small asteroids in unexpected places. NASA is already planning to leverage infrared asteroid detection with the upcoming Near-Earth Object Surveyor mission, a space telescope specifically designed to hunt potentially hazardous asteroids and comets. Combined with Webb's serendipitous discoveries and the MIT team's analytical techniques, these tools will dramatically improve our ability to spot threats before they become urgent. The asteroid belt has revealed itself to be far more complex and populated than scientists realized. The region between Mars and Jupiter contains not just the million objects we've catalogued, but potentially millions more, too small and dark to detect with conventional methods. So what does all of this mean for the future? The 138 asteroids discovered in Webb's TRAPPIST-1 data represent more than just new catalog entries. They demonstrate that cutting-edge technology, clever computational techniques, and scientific curiosity can reveal hidden aspects of even familiar cosmic neighborhoods. For Artem Burdanov and Julian DeWitt and their colleagues, the work continues. They're analyzing additional Webb datasets and expect to find hundreds more small asteroids in the coming years. Each discovery refines our models of the solar system and improves our ability to protect Earth from cosmic impacts. The technique they developed during a pandemic lockdown has become a valuable tool for planetary defense, turning the world's most powerful space telescope into an unexpected guardian against asteroid threats. As Webb continues its primary mission of studying distant galaxies and alien worlds, it will continue to find asteroids crossing its field of view. What were once considered photobombs are now recognized as scientifically valuable discoveries. The smallest asteroids ever detected in the main belt are teaching us that sometimes the most important findings come from looking at familiar things in new ways. Now I want to hear from you. Do you think we're doing enough to track potentially hazardous asteroids? Should more space telescopes be dedicated to planetary defense, or is our current approach sufficient? And here's something worth thinking about. If scientists can find 138 new asteroids just by looking at old images differently, what else might be hiding in data we've already collected? Drop your thoughts in the comments below. If this discovery fascinated you as much as it did me, hit that like button and subscribe so you don't miss what Webb finds next. This telescope keeps surprising us, and we're covering every major discovery as it happens. Thanks for watching, and I'll see you in the next one.